Right, okay, so we're going to look at this example I've got on the board here as an example of using conservation of energy to allow you to work out an unknown value. I'll talk you through the question and we're going to phase in a little bit of work done. So let's go through the question first of all. So here we've got a cart on top of a hill rolling down some track and eventually reaching a speed of 21 metres per second. We've got a mass of our truck of 200 kilograms. We've got an initial height of 50 metres from the final point over there. Now the question is, what is the average force, frictional force, that is done upon the truck going down the track to cause it to be moving at this speed? So what's the average frictional force down the track? So we need to think about what's happened here and we need to think about where we're going. So let's look at the numbers first of all and see if we can just identify what's going on here. Now from the previous video we were able to derive to a relationship that suggested that the velocity after a drop should be equal to the square root of 2gh. And if we plumb the numbers that we've got here into that value, you should see that you get a value of about 31. So what that 31 is telling us is telling us that, oh wait a minute, there's been an amount of velocity that's been lost here as a result of that moving down the track. Now there are a couple of ways of going about this, and I wouldn't start with the velocity calculation. I'm just showing you here that there's been some sort of energy loss as it's gone down the track that's been attributed to that frictional force. So we can use that idea to go from here. So first of all, what I want to do is I want to work out, well, how much energy does it have at the top here? And how much energy does it have at the bottom? The difference is the energy that's lost, because remember, whatever the energy is here should, as long as energy has been conserved, be the energy you get out here as kinetic. So what we look at doing is we do our classic MGH, so 200 times 50 times 9.81, that's MGH. And that's equal to GPE, and that equals okay, 98100. Okay, so that is the energy at the top. The energy at the bottom is our half mv squared, so half 200 times 21 squared. Gives us 44100 joules. Okay, so you're obviously seeing now a discrepancy between those two. You've got 44100, 98100. So if we take one from the other, we get a discrepancy of 54,000 joules. Now, because that's rolled, that's the amount of energy that's missing. Okay, that's the amount of energy that's missing. Because that's what it started with, that's what it ended with. So it's lost that amount of energy somewhere along the way. It should have had a lot more than that. Okay, so where do we go from here? Well, we've got this energy, and we need to work out a force down or up the slope that's in response to a frictional force. So what I haven't told you is the distance down this slope is 100 metres. And that 100 metres, over that 100 metres, this force is going to act opposite to the direction of motion. Okay, it's in the same plane, so it's okay to use the idea of, I'm going to do this in blue, work done. Because work done is force times a distance in the direction of that force. It doesn't matter that the force is opposite, parallel opposite to the direction of motion. It's still in the same plane, so we can use this relationship. So the work done is the amount of energy that's been put in trying to get the cart to stop going down. So it's a frictional force in this direction all the way down. So, what do we know about this? Well, we know that the distance is 100 metres. We know that the work done is the energy that must be the discrepancy energy that's put in to reduce the kinetic energy from what it should have been. And it's that amount right there. So that's the amount of energy that's been put in. So if we rearrange this for force, force is equal to work done over the distance. So that's 54000 divided by 100 gives you 540 newtons. Okay, so 540 newtons is our average frictional force, and that is our final answer to this question. So this is a nice example of a question where we utilise conservation of energy, because the energy's not been lost, it's been transformed into work done on the cart moving in the opposite direction by the frictional forces, and we've conserved all the energy in this whole system because the energy before is the same as the energy after. Okay, what you put in is what you must get out in any form. Okay, so that's a nice example. It's quite a complex example. Do work through it again if you're not sure, and feel free to come with any questions about why anything is what it is, and we'll see you in class with your questions.